Okay, welcome back, everyone. So, what we just wrote down into our assignment is the definition for qualitative and quantitative data. And at this point, we do actually have all of our vocab done for this lesson. That doesn't mean that any lesson that we'll do into this year, that all of it will be done like before at this point in the reading. But for today, that's how it worked out. So, we just talked about what those two types of data are. So, then in 1998, additional modifications were made to the bridge. The bridge that was built in the 1960s did not meet current safety standards. Analysis showed that the changes made to the bridge during this renovation further increased the dead load on the bridge by about 6.1%. So, an early hypothesis. And actually, before I go there, if you look on the side, they've just got some examples of what qualitative and quantitative data is. So, qualitative is there's a thick layer of concrete added to the bridge. Quantitative is saying that it increased the load by 13.4%. The modifications in 1998 increased it by 6.1%. So, those percents, meaning that there was more weight on the bridge, that is our quantitative data because it's a number where qualitative is the qualities of it. And then the last one, at the time of the collapse in 2007, the bridge on the load was increased by another 20%. So, early hypothesis. At the time of the collapse in 2007, the bridge was undergoing several renovations. 4 piles of sand, 4 piles of gravel, a water tanker filled with over 11,000 liters of water, a cement tanker, concrete mixer, and other equipment, supplies, and workers were assembled on the bridge. This caused the load on the bridge to increase by about 20%. In addition to these renovation materials, normal vehicle traffic was on the bridge as well. Did the renovation equipment and traffic overload the bridge, causing the center section to collapse? Only thorough analysis can answer this question. So the hypothesis here is the bridge failed because it was overloaded. So computer modeling. The analysis of the bridge was conducted using computer modeling software as shown in Figure 13. Using computer software, investigators entered data from the Minnesota Bridge into a computer. The computer performed numerous mathematical calculations. After a thorough modeling analysis, it was determined that the bridge was not overloaded. Which in my mind, I'm like, but that means that there must be something else that's happening. So that's how they did their first bit. So now they've got to revise their hypothesis. So evaluations conducted in 1999 and 2003 provided additional clues as to why the bridge failed. As part of the study, investigators took numerous pictures of the bridge structure. The photos revealed bowing of the gusset plates at the 11th node from the south end of the bridge. Reminder, in our assignment, there was something about those gusset plates. So that's why we want to read over those first. Same thing with, like, they said something about that qualitative and quantitative data as well as the variables. So we've got a little preview of those, and we know to come back to those in a bit. So the photos revealed that the bowing of the gusset plates at the 11th node from the south end of the bridge, investigator labeled this node U10. Gusset plates are designed to be stronger than the structural parts that connect it. It's possible that the bowing of the plates indicated a problem with the gusset plate design. Previous inspectors and engineers missed this warning sign. The accident investigators found that some recovered gusset plates were fractured where others were not damaged. If the bridge had been properly constructed, none of the plates should have failed, but inspection showed that some of the plates failed very early in the collapse. After evaluating the evidence, the accident investigators formulated the hypothesis that the gusset plates failed, which led to the bridge collapse. Now investigators had to test this hypothesis. So you can see they revised their hypothesis, and now they need to test that hypothesis. So now testing a hypothesis. So something that you're always doing as a scientist is continually experimenting, looking to draw conclusions. And for this, they didn't find what they needed at the first. So then they're like, okay, if that wasn't it, we need to reformulate and see what else it is. If you're looking to like find a problem, it's going to be a little bit of guess and check. But remember, you can only change one thing at a time. That's kind of their independent variable. Was it the load on the bridge? And they're like, nope, it's not. So now they had to formulate it, and now they've got to look at, was it these gusset plates? When we're doing something more like, is it the head or the tail of the penny that can hold more water? Then we're doing a test at that time, and we're looking to see which answer is correct. So there's a few different ways we can do a test. This is one if they're kind of looking to solve a problem or figure out what had happened. So, testing the hypothesis. The investigators knew the load limits of the bridge. To calculate the load on the bridge when it collapsed, they estimated the combined weight of the bridge and the traffic on the bridge. The investigators divided the load on the bridge when it collapsed by the load limits of the bridge to find the demand to capacity ratio. The demand capacity ratio provides a measure of the structure's safety. So analyzing these results. So if you look on the side here, testing the hypothesis, they want to compare the load on the bridge when it collapsed with the load limits of the bridge at each of the main gussets. They need to determine the demand to capacity ratios and calculate the appropriate thickness of the U10 gusset plates. Their independent variable here is the actual load on the bridge, and the load bridge was designed to handle. And what are they observing? The demand to capacity ratio. So, analyzing the results. As investigators calculated the demand to capacity ratios for each of the main gusset plates, like those shown in Figure 14, they found that the ratios were particularly high for the U10 node. The U10 plate failed earliest and the bridge collapsed. The Table 4 shows the demand to capacity ratios for a few gusset plates at some nodes. A value greater than 1 means the structure is unsafe. Notice how high the ratios are for the U10 gusset plate compared to the other plates. Further calculations show that the U10 plates were not thick enough to support the loads they were supposed to handle. They were about half the thickness they should have been. So now drawing conclusions. So we've analyzed their results. The U10 gusset plates should have been twice as thick as they were. So conclusions. Over the year, modifications to the I-35 bridge added more load to the bridge. On the day of the accident, traffic and the concentration of construction vehicles and materials added still more load. Investigators concluded that if the U10 gusset plates were properly designed, they would have supported the added load. When the investigators examined the original records for the bridge, they were unable to find any detailed gusset plate specifications. They could not determine whether undersized plates were used because of a mistaken calculation or some other error in the design process. The only thing that they could conclude with certainty was that the undersized gusset plates could not reliably hold the bridge. So there's our conclusion, and that's where they ended. The Federal Highway Administration and the National Transportation Safety Board published the results of their investigations. These published reports now provide scientists and engineers with valuable information they can use in the future bridge designs. These reports are good examples of why it's important for scientists and engineers to publish their results and share information. More so, this also shows why you need to make sure you're going through and getting the correct information, because if they would have just ended at the bridge was over, there was too much weight on the bridge, they wouldn't have found that it was actually a structural problem, like a structural problem that caused the bridge to fail. If it was just the load amount, it's like, oh, we didn't build a strong enough bridge. But in theory, they did. There was something specific about how they built the bridge that wasn't good enough. So now we need to answer our questions here. So our first one is distinguish between qualitative and quantitative data. When we add this to our paper, we want to at least have enough information that we can figure out what was our question. So I'm just going to go difference between So I just made it kind of abbreviated. I didn't necessarily write it word for word exactly. You definitely could if you would like to, but at least have the bits and pieces. So either one, we could look at the vocab that we have written above here, or we could go back to that page. So on this page, it tells us that our quantitative data versus our qualitative versus quantitative. So qualitative is using words to describe. Quantitative is using specific numbers. So quantitative. So remember, quantitative, that was saying there was like 6.3% more load, where this is saying buckled. Buckle, buckled. What were those called again? Gussets. Number 2, contrast variable, independent variable, and dependent variable. So, number 2, difference between variables. So we could say that both independent and dependent variables are variables. It's just independent is the one that we change, and dependent is what we're going to observe. Independent and they're our factors in our experiment. So one thing we change. Dependent what we observe is what we observe due to that change. Now, if you're someone who likes highlighters, definitely go for them. You can make this look super nice. Sometimes I like to just have like my questions be one way, and then anything answered that's important. So like, just independent versus the dependent, I might just make that pop out a little bit more. So question number 3. It says, constants are necessary in a controlled experiment because without constants, you would not know which variable affected the what. So I think actually now on mine, because I'd used a marker, it's kind of not easy to read on the back. So I'm just going to use a new piece of paper. Please do use both pieces of paper. Safe paper, it's totally fine. We really can't see it on that side of this. So number 3. So constants are necessary without them, we do not know which variable affected. Okay, so I've got that. I kind of summarized that question just so I have it on here. But then, so constants are necessary. Without them, we don't know which variable has affected the what. So let's go. If you don't remember from the beginning, you could go back to your vocab that you wrote down as we did, or as we wrote it down, or you can go back to the page itself. I think I'm going to go back to it. So experimental group, it's used to study how a change in the independent variable. It says without a control, it's impossible to, whoa, is this literally what it says? So without a control, it's impossible to know whether your experimental observations result from the variable you're testing or some other factor. So our answer then is our experimental group. And that was letter B. Now the best would be if I have an assignment turned in, full sentences as the answers. I do realize, though, that there is a lot of writing here, and so I'm going to expect that there is enough information to have good information. Now, when we're doing a lab, I would expect full sentences. By the end of the year, I'd be expecting to see mostly full sentences. But to get us starting here this year, first step is we need to at least kind of get our feet wet and even know what to do. So, number 4, give an example of a situation in your life in which you depend on adequate testing and evaluation and a product design to keep you safe. So, situation in your life in which you depend on product testing. So, for a question like this, definitely one that could and should be in a full sentence. Now, I'm not going to give you an answer here. I'm going to expect that you pick something and then you add more to it. But some examples that we could think of, what are some things that get tested? What are some products that get tested? Some that I'm thinking are is there something about cars? What about like skateboards or hoverboards? How about food? What about product, as in like shampoo, soap? Whichever one you pick, explain to me why that's important. Again, pause this video if you need to for any of these. On to number 5. It says summarize, so we want to copy and fill in the chart below with a sequence of scientific inquiry steps that was used in one part of the case study. Okay, if you want to make the little boxes with the perfect little arrows, go for it. But what I think I am going to do is I'm just going to go to the very beginning. I'm going to start. So first up, so for what we can write down is steps of science inquiry or testing. So some of these that we need to have, and if we look kind of on the outside edges, it kind of has it for us. So first, we have some observations. So we need to start with some observations so that we know what we might need to test. So we've got observations, and then we have some data, but we have to have a hypothesis based on our observations and possible data that we've gathered. So observations then help to form a hypothesis. And that's going to lead us to having a prediction. Our prediction is more or less the same as our hypothesis. Our hypothesis is like an educated guess. It's not like what caused the bridge to fail? Oh, I think Sasquatch stood on it. Okay, yes, it's a guess, but it's not an educated guess. Sasquatch may or may not be real, but he definitely was not on the bridge that day. So an educated guess would be like, oh, there was there were too many cars on the bridge. Oh, there was something in the design of the bridge that failed. Maybe they were going to they did look into weathering and erosion. Did that have an impact? It could be something about like there's water underneath. Was the soil degrading underneath? Like it had a bad foundation. Those would all be quality educated guesses. So after we have our hypothesis, we need to test what's happening or experiment. And then we've got to analyze our results. My paper is not quite long enough because our last thing is our conclusions. And if at any point any of these are not correct or it doesn't give us information that's correct, they loop back and they start again. So when they thought it was just shear, there's just too much weight, and then they found out after experimenting that it wasn't just the weight, they had to go back and make a new hypothesis until they're like, yes, this all fits. If even one piece of the puzzle doesn't fit, you haven't answered your question. So that's number 5. Number 6. We want to analyze how a scientific inquiry process differs when engineers design a product, such as a bridge, and when they investigate design failure. So, process for design a product versus product failure. So what would be the difference between them testing their product versus investigating for failure? When we design a car, they do numerous crash tests because they're looking for every possible situation that it could fail. When they're looking at product failure, it's failed. So they know where it's failed. Now they need to figure out how to recreate that failure and how can they explain what has happened. So when they're designing a product, they're trying to make it fail. And when it's product failure, we need to find why this happened. Now, when designing a product, you want to try and make it so you will never have to investigate product failure. If you've designed a product and you have put it through enough of testing of that product, then design product, then you shouldn't have failures. However, we don't live in a perfect world. We know that right now with what our current situation is. So we're never going to find every bit of failure. But when we do find failure, now we need to figure it out and figure out how we can make it so it doesn't happen again. So number 7 then. Evaluate why the gusset plates were such a critical piece. Why were So again, you can kind of abbreviate that. So why were these gusset plates so important? If we go back to, let's see, it was this page, and they had this picture. These gusset plates is where everything is meeting and getting held together. So this type of bridge, remember, is formed by different rods and different angles, all coming together, and they're supporting each other to make a very strong bridge, but it's all being held together by those gusset plates. And if those gusset plates can't hold together all of the parts, if those fail, then nothing else is able to be held together. So when we're writing down why were the gusset plates so important, that was holding. And actually, you know what? We can make this better. Instead of saying that, that's not how we write a complete sentence. The gusset were what was holding the parts together to make a strong bridge. So that's why, like, the beam bridges, why those aren't very strong is because those spans are so long and they sag in the middle, where a gusset bridge, or a bridge that uses gussets, it has all these interconnected rods and pieces. Each rod is not all that long, so each rod, it's really hard for each rod to bend. It's really hard for each beam to bend when it's being supported by so many rods. But if, like, the glue holding it all together isn't working, then it's not going to do much good. So then the last one is recommend ways that bridge designers and inspectors can prevent future bridge collapses. So number 8, how can future bridge collapses be stopped? Now, this is going to come a little bit from yourself. So you need to come up with this. You decide and explain. But here's some things that we can think about. They mentioned that this is in Minnesota, where Minnesota gets a lot of snow and they use salt to de-ice the roads. So if there's a bridge getting built in an area such as Minnesota that's going to have ice and there's going to be salt used, they probably want to use proper materials. I mean, this bridge collapse was it was an absolute tragedy. There was not much good that came out of it. The good that came out of it is knowledge of how to make a better bridge in the future. So they can see in the future if there's ever going to be a bridge built where salt is being used often to de-ice the roads, they want to make sure they use the correct materials because they were putting concrete on top of the metal to help it from eroding. Well, maybe they don't want to use that type of metal so that it doesn't erode, or they want one that the salt won't erode it. Something else that we might want to think about is what materials are going to be better. Are there ones that are more sustainable? Maybe they're going to see like, hey, they didn't use these gusset plates that were thick enough. So when they go to build a bridge in the future, they use one that is thick enough. Something else that was a consideration here is this bridge was built in like the 1960s when there was a different amount of traffic flow. So when they build a bridge, they don't want it to maybe meet the needs of today. They want it to meet the needs of 20 years from now when there could be more traffic because the world is ever changing and progressing, and anything we do today, as soon as it's built, it's already out of date. Anything's like that because our world is continually progressing. So that might be something that they want to consider. Something else they might want to consider, you might have heard me say, like, was the foundation of the bridge okay? So they've found that to be a problem where like the foundation itself is just sinking into the ground. There's another bridge, if you look it up online, that the bridge, how it was made, when wind was being blown across it, it started warbling and it totally twisted itself apart. And they now are like, "Ooh, probably don't do those types of bridges anymore." So there's never like one way you could say. That's why you get to decide and explain it here. So put your answers there. I'll be looking forward to reading that. But you might even have another way that they can make bridges safer and better in the future. Looking forward to seeing this and all your other things. Now, the last thing you need to do is take pictures of these assignments. Now, options that you have. You could, if you have a phone, use your phone to take pictures, and if they're on both sides, make sure you get all the sides, okay? If you don't have a phone, guess what? You have a Chromebook, and your Chromebook has a camera. Now, okay, I get that it's not going to be like super perfect, but you can take a picture, like have your camera up, right? So I guess here, if I like embarrass myself, I can do something like this and make sure it's all in. And if I want to make sure I'm not on camera, I could do something like this and then take the picture, turn it, take the picture, right, and get all of my pictures taken then, but make sure those get uploaded so that we can see them. Also make sure they're not blurry, because if they're kind of blurry, we can't really see it, and then we can't really give a grade, or you haven't really earned credit because we can't see if you've earned any credit. So big things, get the vocab, then answer the questions at the end of the lesson. We're going to have more of these coming up this year. This one we did together. It did take a little while, but we want you to be super successful. Let me or your science teacher know. This is Carpolinia. If you have any questions, have a great day, guys. Bye.